Our next speaker is Dr. Alex van Leeuwen. Alex finished his PhD in the last couple of years at Uni SA, where he applied petrochronological techniques to investigating the metamorphic evolution of the Kerner-Mobinet province. And he's currently, we're lucky enough to have him as an embedded researcher at the Geological Survey, working at the University of Adelaide as part of the MINEX CRC, and he's focusing on the gold mineral systems in the central western Gawler Craton and advancing the development of a range of petrochronological tools. Welcome, Alex, please.
Thanks, Liz, for the intro. Over the next little while here, I'm going to be giving a bit of an overview of some of the work that we've been doing. It is really bright here. That in the central western Gawler Craton. So this is work that's been done in collaboration with GSSA, Uni Adelaide and Uni SA as part of MINEX CRC. And I want to just sort of explore, I guess, the interplay between metamorphism and gold mineralisation that we see in the region, and some insights that we've been able to garner from some sort of more novel geochronological techniques. I'll just jump right into things. A bit of an overview of the regional geology. So here on the right-hand side, I have a total magnetic intensity map of the broader central western Gawler Craton, and I'll really highlight the region outlined in the bold white line, and that's the Christie domain. So the Christie domain is one of three subdomains that comprise the broader Mulgathin complex. So the Mulgathin complex hosts some of the oldest rocks in the Gawler Craton, and they were deposited and placed anywhere between 2555 MA and 2470 MA, so late Archean to early Paleo-Proterozoic. Lithologically, they're quite complex, but in the Christie domain, which is sort of the focal point of this study, they're dominated by metasedimentary rocks. And metasedimentary rocks that have been metamorphosed up to granulite facies. So you can see on the left-hand side image a photo of a piece of core, actually from Challenger, which is one of the study areas. Quite a nice garnet biotite, migmatite. And these rocks were metamorphosed at about 850 degrees, so quite hot. And I guess another thing that you can see is I've plotted all of the regional gold prospects or gold anomalies that have been drilled in the region. So there's quite a lot of them, and we've sort of chosen two, Challenger and Gulf Bore, to really compare with one another to see what this gold province actually looks like. Most of the work that's been done previously has been centered around Challenger, and we want to see if these models for Challenger really fit the more regional framework. So the current school of thought is that gold mineralisation occurred either prior to or during the very early stages of the Slifordian orogeny. And I should say that the Slifordian orogeny was really the event that metamorphosed these rocks up to granulite facies and formed these really nice isoclinally folded leucosomes and these cool mineral textures that we see. But yes, the importance of this event is not well constrained throughout the region. And lastly, in terms of the regional geology, I should just say that the region is dissected by a series of northeast, southwest trending shear zones that were active during the Kimber orogeny, so between 1730 and 1690 MA, and potentially reactivated later than that too. So I should say, well, actually I'll go to the next slide, where I'll give a bit of an overview of the general mineralisation model, or gold mineralisation model for Challenger. As I say, most of the work that's been done in the region to date has been using this as a model for all of the gold mineralisation in the region. So I'll go through this as sort of a cartoonised set of diagrams that I've compiled from the work of Andy Tompkins and Chris McFarlane throughout the 2000s. So from left to right, from oldest to youngest, initially we have the intrusion of some gold-bearing quartz veins, gold being primarily hosted in sulfides, primarily arsenopyrite. And during the intrusion of these quartz veins, we also bring fluids into the system, and they form alteration halos locally surrounding these quartz veins and form mica-rich mineral assemblages that, importantly, are much more hydrous than their unaltered counterparts, which are the protoliths, really, to the Christie gneiss, which are these metasedimentary rocks. So if we fast forward into the Slifordian orogeny proper, which is the latter two panels here, we see we have two things happening in tandem. We have both deformation of these quartz veins where they're being transposed into parallelism with the regional metamorphic fabric, which makes discerning what's a quartz vein and what's a leucosome really quite difficult until you get down to sort of a thin section scale. And you also have partial melting of the succession during metamorphism. And what we see is that partial melting is really focused in these alteration zones. And that really leads to, I guess, the misnomer in terms of the classification of these type of deposits as there being migmatite-hosted gold deposits, implying that the partial melting process has a sort of primary control on gold mineralization, when in reality it's just a product of this previous alteration that was imparted during the primary mineralization phase, and then during high temperature metamorphism, these generate more melt just due to the fact that they contain higher water contents, and therefore they will melt more effectively than their unaltered counterparts. So that's really the model for Challenger. And as I say, what we want to do here is look at Gulf Bore, because we have some nice drill core from Gulf Bore. Drill core is quite sparse, as Frank showed, it's quite sparse throughout the whole Gawler Craton. So we have a nice drill intersect at Gulf Bore, and we want to compare that with what we see at Challenger. So answering this question here, is the paragenesis that we see at Gulf Bore similar to that at Challenger? Or is this gold-bearing migmatite from Gulf Bore the same as a quite similar looking gold-bearing migmatite from Challenger? So in order to tackle this problem, we first went to doing some monazite uranium lead dating. Monazite's quite ubiquitous in these granulite facies rocks, so it's a pretty logical place to start to compare the two deposits. We dated probably 10 to 15 samples from both of these deposits to really build out a nice framework, but I've sort of cherry-picked these two samples here, one from both deposits, to sort of highlight the general geochronological framework. So I'll just go through this. I won't explain too much about what the data is exactly showing, but in terms of the geochronological interpretations, we see we have three main populations of monazite. So we have an early history that's recorded in rare, this is the laserite. I don't know if this comes through very well, but there are these dark cores that are quite patchy, quite small, quite irregular. And when we've been able to target these yield quite old ages, around 2470 to 2460 MA. And we think this dates the timing of sort of the onset of metamorphism, so the beginning of prograde metamorphism during the Slefordian orogeny. And then we come to these blue ellipses, which are the most dominant throughout the region in terms of both their abundance and in terms of volume of monazite grown. And we think these relate to the timing of peak metamorphism and the real thermal maximum and the generation of the most volumes of partial melt. We see that both at Challenger and Gulf Bore, and more regionally, other workers have seen this throughout the Mulgathing complex. And interestingly, we see a younger age, mainly recorded at Challenger, in a series of thin rims on quite large monazite grains, and they yield an age of 2420 MA. And we think this relates to cooling through the solidus and crystallization of melt in the system, and really the final phases of the final phase of the Slefordian orogeny. So that's all good, that's cool, a nice little study, and it confirms really what other people have done in the region earlier. But based on this data alone, you would just say that Challenger and Gulf Bore are more or less equivalent. They have a shared history, etc. But what we do see at Gulf Bore, which is very much absent at Challenger, is we see monazite analyses or grains which have intercepts or have ages that are around 1700 MA. Now, these data are not particularly convincing for the geochronologist in the room, but it's a hint at there being a fingerprint or an overprint, sorry, at Gulf Bore, which is not present at Challenger. I'll get you to ignore this spurious upper intercept age. We've confirmed this age in a few samples from Gulf Bore, but once again, they're very rare grains and it's very, very spurious. You wouldn't want to bet the house on this being a real thing based on these data alone. So that really made us want to explore this and see if we can extract this age more convincingly and really tie it to things that are actually happening in the rock. A bit more about the overprint story. So here's a full thin section photomicrograph from the ore grade sample from Gulf Bore. And what I've annotated the margin of a leucosome, a Slifordian age leucosome, in these blue dashed lines, and on either side we have similar Slifordian aged mineral assemblage, biotite, quartz and feldspar. But what these red arrows point towards are arsenopyrite grains. These are the main host of gold in these rocks, is the main sort of ore mineral, I guess. And they contain inclusions of the matrix minerals within the Slifordian age matrix minerals, which sort of suggests that these arsenopyrite grains, in a relative sense, are later than the Slifordian aged fabric in which they're growing. And we also see a series of veins, or veinlets. So we have these pyrrhotite-dominated veins, and we have these sort of fine-grained pyrrhotite, sphalerite, mica-rich veinlets. And these both form at high angle, or they cross-cut the Slifordian age fabric. So we have sort of, in terms of relative chronology, we have an idea that there is a later overprinting event here at Gulf Bore, which is not seen at Challenger. Now, obviously, without assigning numbers to this could be just during the very late stages of the Slifordian, or it could be, yesterday, really, or whenever they drilled the hole. But really we wanted to assign some ages to this and be convinced that this is a real overprint. So, first of all, I wanted to look at some of these sulfides in a bit more detail to see if they show any sort of interesting characteristics in terms of the actual ore genesis. So here's just the same photomicrograph, and I've just shown a picture of the sulfide that we decided to map. This is a nice arsenopyrite grain hosted in this Slifordian leucosome. And I've changed the colour scheme and rotated it just so it's super annoying for everyone viewing. But here's what that grain looks like in a bit more detail. Some of these are a bit washed out, unfortunately, but up these top two images here are really the important ones, the cobalt and nickel, and our gold map down in the bottom right. And you could be here for quite a while looking at the different zoning patterns and so on, but just broad strokes, you can see there are two main generations of arsenopyrite here. We have a high cobalt, high nickel core, and we have a comparatively low cobalt, low nickel rim, which mantles it. And when we look at the gold map, we can see that the gold is almost solely hosted in these low nickel, low cobalt, second generation of arsenopyrite, suggesting that gold in this sequence is coming in later than the first phase of arsenopyrite growth. So all these things together sort of suggest that we have at least some mobilisation or remobilisation of sulfides, and we really want to, I guess, answer this question. Can we constrain the timing of this sulfide remobilisation and the timing of the overprint? So, to do that, we went to one of these novel geochronological methods that's recently been developed at Adelaide University, and that is dating garnet using lutetium-hafnium, using the lutetium-hafnium isotopic system, and that's being able to be done in situ now. So here is a sample only about 10 metres downhole from the previous sample that I showed you, the high-grade ore zone. And we're fortunate enough to find a sample that contains two quite clear generations of garnet. So you can see here on the left-hand side, we have quite an anhedral, quite a corroded, embayed garnet. Looks quite unhappy. This is our first generation of garnet. And then on the right-hand side, we have, in a relative sense, a much more euhedral, nice-looking garnet that appears to overprint the metamorphic fabric. And you can also see that the inclusion assemblage in these two garnets are quite different. So it's convincing that they're quite different, but just to be even more convincing, we mapped some of these garnets isotopically using a laser ablation ICP-MS at UniSA. And we can see, here's that first garnet that I showed you, the first generation, here's the second generation, and these are the calcium compositional maps, I should say. And you can see that the calcium content of this second generation of garnet is much higher, and you can even see small rims forming on this first generation of garnet. And here is a nice composite grain, which I'll show in a bit more detail, where we have the low calcium core, our first generation of garnet, being mantled by a higher calcium rim. So here's that map in a bit more detail. Once again, I've changed the colour scheme just for everyone's viewing pleasure. And this first done myself a mischief here. There we go. So the first generation of garnet shows two sort of key features. We can see on the yttrium and heavy rare earth maps that we have these quite distinct linear features. It gets a bit muddled up, but in some places you can track them and they sort of trace out sort of the crystal habit of a garnet. And that's usually, this is something that you'd call an annulus or a satellite peak, and these usually form in metamorphic garnets that are growing when another phase breaks down and liberates heavy rare earths and so on, and it's sort of a transient spike that happens as garnet continues to grow. And we also see these hotspots So this is probably an aggregate of several garnet grains, but we see an elevated core domain, and then that depletes radially outwards towards the rim. And this is another kind of hallmark sort of thing you see in pro-grade metamorphic garnet. So this sort of is suggestive that these garnets grew in a metamorphic environment. But when we look at the second generation of garnet, which is this rim here, you can see quite nicely, the zoning patterns are quite chaotic. It's very irregular. There is really no pattern to it. And these sort of textures are quite common in rocks that have experienced fluid rock interaction or have been hydrothermally altered at least. So there are two sort of quite distinct textures here, and we wanted to see if we can date them and constrain their age. So we did that. And here's what the data looks like. So here on the left-hand side, we have an isochron plot, an inverse isochron plot of the garnet data, and you can see there are two very distinct isochrons. We have this low calcium trend and this high calcium trend. So the first generation of garnet and the second generation of garnet. The first generation of garnet comes out at about 24, 25, so right on the tail end of the Slefordian orogeny. So that's a good line of evidence that this is a metamorphic garnet. It grew during this granulite facies metamorphic event, the Slefordian. But we also see that this high calcium trend yields a 1730 MA age, and that's quite convincingly in the Kimban orogeny, right at the beginning of the Kimban as it's currently defined. So not only do we have evidence for the Kimban orogeny, but we also have textural evidence from the garnets that this was a hydrothermal event, not just an overprinting metamorphic episode where just solely heating. You actually have fluids being introduced into the system. So I'll end on this slide here where I'm just going to speculate rampantly about links to the central Gawler gold province. So what we see in this, this is an interpreted seismic section from the Euclid-Gawler seismic line down the bottom here. And what we see, I don't know how well this is being picked up, but you can see that the crustal scale shear zones that dissect the Christie domain, they penetrate through the crust and they actually tap the mantle. They penetrate into the mantle lithosphere. And some recent work that's been done actually this year by David Groves has found that in the central Gawler gold province, they prefer a model where you have, instead of a crustal fluid source for orogenic gold, you have a mantle-derived source for orogenic gold. And they propose that things like the Yalbrinda shear zone that Frank was just talking about, these structures which may intercept the mantle may be a mechanism to extract fluids from the metasomatized mantle lithosphere and bring them into the mid to upper crust and form gold deposits. And although the Yalbrinda shear zone, the shearing in that system is younger than the Kimban in theory, I'm not sure how well constrained that actually is, but it's been proposed to be sort of Hiltebert aged. I see no reason why these shear zones that are tapping the same metasomatized mantle which underlies the Gawler Craton can't be mobilizing fluids from depth from the mantle and generating either new gold deposits or remobilizing existing maybe Challenger style ore systems. So with that, I will leave it there because I think I've gone well and truly over. So I'll just leave on this summary slide. I won't read that out. And thank you all for listening, and thank you for inviting me.